So combinations, permutations, this is something you did in grade 12. You've come across a couple of these things already in your math labs. And it comes up again here, so we look at a few things. First of all, a notation thing for IB is they use, for combinations, the n over r in brackets. What did you use last year? NCR. Okay, so those things mean the same. So if you have a 5 over 3 like that in brackets, that means 5 choose 3. Something about combinations. If you have 5 choose 3, the 5 factorial will be on the top, the 3 factorial would be on the bottom. How do you know the other number is 2 factorial? Those two add up to the one on the top. And then you can expand the bigger one. 5 times 4 times 3, and when you get to 3, it cancels out with the 3 factorial on the bottom. Just gives you 5 times 4 divided by 2 is 10. So, mental math, do the rest. I'll give you a minute head start, 15 seconds for each one. All right, that's about a minute. 10 choose 2. Did you get 45? Expand the bigger one until the 8s cancel out. If it's 10 choose 2, there'll be a 10 factorial on the top, the 2 factorial on the bottom, and always what adds up to 10. So 10 choose 8, same as 10 choose 2, so hopefully you got the same answer even quicker. 7 choose 0. Do you remember the definition of what 0 factorial is? 0 factorial is equal to 1. That's by definition. It doesn't work with the formula. Remember, a factorial says start with that number and subtract 1 and keep multiplying until you get down to 1. Well, that doesn't work with 0 factorial. And so by definition, it's 1, and this just becomes 1 in the end. 100 choose 98. Expand the bigger one. Divide by 2. 4,950. Pascal's triangle. 1, 1, 1. You remember how to find the next row? 1, 2, 1, 1, 3, 3, 1. Yes or no? If I did one more row, the next number would be 1, then 8. 28. 56. 70. Just adding the 2 above it, right? So cool. So many neat things in Pascal's triangle. Just for fun, just because it's like, if you make a shape of numbers that's really cool, they name it after you. Lucky Pascal made this shape. One of the applications we're going to get to next is expanding or developing binomials, because the coefficients are in Pascal's triangle. Here's the easy one. What's x plus y squared? It's x squared plus 2xy plus y squared. These numbers here, 1x squared, 2xy, 1y squared, they come from right there, 1, 2, 1. If you did x plus y cubed, it would be x cubed plus 3x squared y plus 3xy squared plus y cubed. Comes from those numbers. Now, for those of you that were in my class last year, I probably showed you some of the cool things in Pascal's triangle, but for those of you that weren't, some other things that are neat. Okay? First of all, if you add up the numbers in each row, you get the powers of 2. 1, 2, 4, 8, 16, that's a 3, 32, 64, and so on. And that keeps going. So if you didn't know that, that's a cool thing about Pascal's triangle. Another cool thing about Pascal's triangle, if you think of them as numbers, 1, 11, 121, 1,331, 14,641. Anybody recognize those numbers? Probably not. Those are your powers of 11. 121 is 11 squared. This is 11 to the 1. This is 11 to the 0. This is 11 cubed. This is 11 to the 4. And then here we run into a problem. Well, not a real problem, but we have tens. Those don't really fit in digits. So you have to carry the 1 over here, which makes this 11. Carry the 1 over here. 1, 6, 1, 0, 5, 1. Check that out on your calculator. Sure enough, that is 11 to the 5. And if you would do that with this one, 1, 6, 5, carry the 1 over 21, carry the 2 over 17, carry the 1 over 7. That's 11 to the 6. Very cool. But the coolness doesn't just stop there. Oh my goodness. If you choose a very strategic line, yeah, that one. If you choose that line, and start at the top, you hit one number, then you hit one number, then you hit 1 plus 1, adds up to 2, then you hit 1 and 2, which makes 3, then you hit 1 and 3 and 1, which makes 5. Does anybody know what those numbers are? Next one is 8. They're the Fibonacci numbers, which are super cool. And if I start talking about them, then we're going to take, I'm already getting off topic on Sierpinski's triangle. I can't get off topic, so there we go. I could, but I'm not going to. I'm going to try to be good today. Okay, so there you've got the Fibonacci numbers. Excellent. And finally, I will get a little bit off topic on the next one. Let's just erase some of these. There we go. And finally, if you would keep making Pascal's triangle bigger and bigger and decide to shade in the even numbered ones forever and ever and ever, and so on, it makes Sierpinski's triangle. What is Sierpinski's triangle? Well, here I'll pick a color and I'll show you Sierpinski's triangle. And we'll do a fast version rather than slow. What color would you like? Red. There's a magic. There's the red version. There's Sierpinski's triangle. Of course, it's flipped upside down with Pascal's triangle. And if you kept making Pascal's triangle bigger and bigger and bigger, and with a black marker shaded all the even numbers would be blacked out and all the other numbers would show up in red. Magic version? Ooh. Oh. Okay. What's happened with this program? A computer science student made this for me. There's a slow version, and while it's slowly going, I'll describe what's happening. This program was made by having 3 vertices of an equilateral triangle. Okay? And you can imagine, for example, something random like rolling a die. 1 or 2 is associated to the top left, 3 and 4 to the top right, 5 and 6 to the bottom. What happens is you randomly pick a pixel anywhere on the screen. Oh, something stopped working. Hit back. Oh, project. See, got to close it. Anyways, so you randomly pick a dot anywhere on the screen. Let's go. Blue's pretty. You randomly pick a point anywhere on the screen, and then a random number is drawn. So for example, I can't quite tell where this one started, but whatever number is picked, you draw the midpoint from where you were to that vertices. So if I was started here and I rolled a 1, I draw a dot halfway to 1. And then if I rolled a 3, I would draw a dot halfway to 3. Then halfway to whatever's, if I rolled a 3 again, halfway again, halfway again, halfway again. And this randomness is done over and over and over again. And no matter where you pick your point on the screen, this is what always appears. Even though you do something random every single time after that. Here, this is a good example. Oh, this is really nice. I can tell exactly which numbers were picked first. Here's the point that was random. And then they rolled the 5 or 6, went here. 5 or 6 was rolled again, went there. Then the 3 or 4 was rolled, went there, halfway there, halfway again, and then this number was rolled and the point got inside the triangle. As soon as the point gets inside the triangle, it can never get out again. It's trapped. Yes. This is the point trapping mechanism. And what's cool about this is that it always makes the same shape. So this is a mathematical sort of model or application for maybe what they think happens something in biology. How is it that a small seed always produces the same plant? There's not a lot of information on that seed, and yet it does the same thing every time. And yet it's not quite the same, because we don't all look the same in here. We're somewhat different looking. Okay? But nobody turned out to be, let's pick a random animal, a lemur, right? Wouldn't that, like, it just be so awkward, right? Everybody in your class is human, and your friend's parents had a lemur. They don't know what happened, but something happened. Okay? So why is it that a fern seed always produces a fern? And so this is kind of a model that says, well, maybe there's information that's somewhat random, but a pattern-like thing to do, that it always produces the same thing. And they've created similar random things like this that make a perfect fern leaf and other stuff. Anyways, that is totally off topic. Now I'm going to get back to somewhat off topic. We started with our Pascal's triangle. And then really back to on topic is figuring out, oh, did I skipped one. Let's do it quickly. X plus y to the 5. You will have x to the 5, x to the 4y, x to the 3y squared. I'm missing the numbers in front. I know I'm running out of room. So in an expansion of x to the 5, you will have 6 terms. Do you remember that? You always have one more term than whatever the exponent is. I'm going to turn the light back on. Brace yourself. And then the coefficients for this one will come from this row right here with 6 terms. 1, 5, 10, plus sign should be there, 10. Oh my goodness, was I bad with my plus signs? 5, 1. And so the coefficients come from Pascal's triangle. The coefficients come from combinations. Again, you have learned this already, but a little explanation of what's happening when I multiply x plus y to the 5th, just to help you understand why the combinations are there. What happens is a lot of multiplications happen. In fact, if you drew some weird, you know how when you multiply 2 in English we say you FOIL, right? Because those are all the possibilities. When you have a bunch of them, there are tons of possibilities that come through. You could have multiplied the x, the x, the x, the x. That happens to be x to the 5th. Now, that's the only way you can draw, I'll call them hops, jumps, bumps, whatever. Okay? That's the only way you can get all the x's in that pattern. But if I want 4 x's and 1 y, can you see that I could get my 4 x's this way and then my 1 y? Or I could have got my 4 x's by, that's my 1 y. Oh, there we go. That's a bad hop. Okay? And we could keep drawing this. I could skip the first x. There we go. Or I haven't skipped the third y. There we go. And we could count that, and you would get 5 of them. Why does it come out to be 5? Well, in this example, I could think about my y's. I want 1 y. How many y's are there? There's 5 of them. 5, choose one of those y's. Okay? 5, choose 1 y. Comes out to 5. The next number is 10. Why are there 10 x cubed y squareds? Well, how many ways could I choose 2 y's? 5, choose 2. 10 ways. That's in those hops, bumps, skips, jumps, whatever you want to call them. If you drew all the paths, you would get 10 of them that have 2 y's and 3 x's. And what's really neat is I've been talking about the y's, but 10 choose 2 y's is the same as 10 choose 3 x's. Those numbers are the same. So you could think about the x's or the y's according to how it's written here by starting with 5 choose 0, 5 choose 1, 5 choose 2. It makes sense to think about there's 0 y's here, 5 choose 0, 1. 1 y, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. Okay, that's all review. Maybe, most likely though, if I explained it to you last year or Mr. LaFrance explained it to you where it comes from, you've probably forgotten that and just worked with it. But it's sometimes nice to see where does the idea come from again. On your IB formula sheet, okay, it's different than your pre-calculus formula sheet. On your pre-calculus formula sheet from last year, you had this. For term k plus 1. What you need to recognize is that this formula here is the same as this part on your formula sheet for IB. Instead of k, they use r. Ooh. Is that going to be okay? You going to be able to handle that? Okay, so that's first change. Then they don't tell you it's term k plus 1. They just say, here's term 1. Here's term 2. Term 2 has a 1 at the bottom. So if I have an r at the bottom, this has to be term r plus 1. So it's inferred, whereas on your pre-calculus formula sheet, it was explicitly told to you which one it was. But other than that, that part of that formula is the same. So it is important to know how your IB formula sheet works so you can pull that out of there and be able to work with it. So if we want to find the 7th term in the expansion, that would make R 6. So you have 9 choose 6. 2x is your first term to the power 3 minus 3y to the power 6. In an expansion, they give you lots of marks because they give you a mark if you, did you get 84 right? Did you expand this one right? Did you expand this one right? And then did you get the right final answer? So, what happens if you're like, oh, I forgot negative to the 6 and I accidentally put a negative there? You would lose the mark for this. And then what would happen in your final answer? You would still have a negative there. They would take off another mark. There, 2-mark mistake. So as opposed to pre-calculus, where you would get 1 mistake for a silly error, and then they would say, but you've done everything else right, so we'll accept it. On an IB test, 1 mistake for the error and an additional mistake for not having the right answer in the end. Okay, don't copy those negatives. They're not right. Whoa. There we go. Yes? That's right. Because just like your formula before was tk plus 1, now it's tr plus 1. It's always 1 less. And the hint for 1 less is told to us in term 2 that that's a 1. That's how they tell you it's 1 less on the IB formula sheet. It's recognizing a pattern. Find the term in y to the 12 in the expansion of this. So, probably before this, I would write out my formula. I don't know which term it is, so I wouldn't know what r is. And I'll write this off to the side here. Your formula would say you have 9, choose r, 3x to the 9 minus r, and negative 4y squared to the r. Then analyze, and if you'd like to, you can even write this as term r plus 1. Then analyzing the right side of that equation, can you see that the only place that there are y's are right there? And if I wanted to get a y to the 12, r would have to be 6. Oh, I better not put an exclamation mark. Whew. Thank you. And then once you find out that r is 6, it's term 7. Multiply everything out and get your answer. This one, so these questions that say find the term containing y to the 12th or in y to the 12th in the expansion, these are a little bit more complicated because we have to find the r value first to help us find out which term it is. This one was easy because there was only one place where there was a y. Yes? You can use the old formula. It is exactly the same, right? Yeah. And you won't be deducted for using different notation. So if you like the n, choose k as opposed to the brackets. Okay? I remember when I learned this notation, just curious if this happens to any, well, you haven't done it enough. You haven't really used this notation very much, but this always happened to me. I'm like, oh, I drew a fraction. You just did that. It's right there. Because that's what happens when you write numbers over. You're so used to writing fractions. Like my notes had this in it all the time. Okay, and it's going, obviously, since it's already happening to you, either welcome to the weird club or it's normal. Find the constant term. What is a constant term? A one without a variable, okay? And another way that we can think about that, if it has no variable, or it could have a variable x with an exponent of 0. If it has no variable, well, an x to the 0 would make that go away. Now, in this case, again, this is the letter R. I'm going to make it nicer. Is it nicer R? There we go. Just so it fits our formula sheet. Oh. a little bit more. Beautiful. If we write it out like this, what we need to happen is for all of our x's to cancel out. Now there's a couple ways we could go about this. Okay? First of all, we could ignore all the numbers in front. Numbers in front, what's the math word for that? Ignore all the coefficients. So the 14 choose r is going to be a number. I'm going to ignore it. The 3 is going to be to some exponent. I'm going to ignore it. The negative affects the number in front. The 2 on the bottom affects the number in front. I'm just going to think about the x to the 5 in my denominator and take out my eraser again and make these r's. Beautiful. That's actually quite enjoyable, erasing part of an n to make it into an r. Once we have this, you can use your exponent laws. Exponent to an exponent means that you multiply and then dividing your exponents means that you subtract. Beautiful. And solving that equation, once you've got your left-hand side to a single power, x to the power of 28 minus 7r, and the other side is x to the 0, it will have to be that your exponents are the same. And then it becomes easy to solve that r must be 4. And once you've solved that r is 4, it's a matter of then plugging that into your equation to find term 5. Sure enough, everything in term 5 for the x's cancels out beautifully. And we get a very nice big large number with a decimal point right there. Perfect, perfect, perfect. So you could use your exponent laws to figure it out. Okay? Some people get very good at just looking at the equation and figuring out what works. So I know that the answer is 4. Okay? We've solved it. We know that the answer is 4. If I was trying to guess and check to find something that works, again, I'm ignoring all the numbers in front. I might choose a random number to start with, like 6. If you chose 6, can you see that 14 minus 6 would be 8, which would give you x squared to the 8. If r equaled 6, I would get x to the 16 on the top, and if r is 6, x to the 30 on the bottom. What's the problem? Too many numbers on the bottom. How do I remedy that? I need to make r smaller so I don't have as many numbers on the bottom. And I'll tell you, with that, just trying a couple of numbers and using regular logic, not probable logic or anything like that, just regular logic, you'll quickly find out that r is 4 without having to do the algebra all the way through. That would be fine as well. Yes? The negative 1 is going to affect the coefficients. I still technically have the 1 on the top of the fraction because my x to the 5 is still on the bottom of my fraction.
Yeah, which is like why I'm confused why it's not negative.
The negative is going to affect the coefficient.
But it won't affect the
It won't affect the x's, right? So these questions that we've done so far, these have all been a review of grade 12 questions. Okay? Now, over the past 5 or 6 years, the interesting thing is, of all the parts that they like to be creative on the IB exam, the binomial expansion is one of them. So we're going to also look at what do creative questions look like in binomial expansions. Okay, this one, not creative yet. This one's just straightforward. Write down the number of terms, always one more than the exponent 7. Which one has an x to the 12? Okay, here's your formula. Oh, I still like, just so it matches up with your formula sheet, I'm going to, no, not because it matches up with your formula sheet, just because I like erasing parts of n's to make them into r's. We'll make those r's again. I don't think I'd be having this much fun if my toe hurt more. And here, again, you can do the math where you ignore the coefficients, but see if you can figure out what r is going to be. You want an x to the 12. Can you put in some numbers for r and see which one works? Boom, got it. Did you do mental math? Did you see that r equals 3 works? I mean, we can do the expansion and enjoy the fact that we can erase these n's. And you could figure out that r is equal to 3. But just looking at the equation and trying some numbers, you could probably mental math figure out that r is 3 just as fast. So if r is 3, we can now go back to our formula, plug in everything, and find the actual term.
That's 18 minus
18 minus 2r, because this negative 3r plus r would give me negative 2r. Yes. I can go back. I went so fast because I want to get to the harder questions. Yes. All right. Question 5. Partially creative. Not super creative, but a partially creative IB exam question. The fifth term is given by 10 choose 4, p to the 6, 2q to the 4. What's the value of n? 10. Makes sense that whatever your 10 choose 4, that 10 is your exponent n. Write down a and b in terms of p and or q. Okay, this is just, can you see that a is whatever number is here, b is whatever number is there. So this is partially creative, but it wasn't really hard, just kind of a little bit awkward kind of question. So partially creative just because they added some awkwardness to it, but just saying, do you know where the things in the formula go? Not really hard. In fact, probably easier than you think it should be. And sometimes I will say that you'll find that on IB questions. You will get a question that in the end it feels like, that was too easy. I should change it and do something harder. Don't do that. They will do those kind of questions. They will give you a way too easy question just so that you question yourself, can it really be that easy? And the answer is sometimes yes. And later on, you will ask yourself, could it really be that hard? Yes. They'll do that too. Sometimes too easy, sometimes too hard. Just to, I don't know. Just to be like, you have to be really, we want you to be really confident in your skills that when it's too easy, you go, yes, that's too easy. I'm sure that that's what it is. And when it's too hard, you're like, yes, that's too hard. And we can move on from there. And then writing an expression for the sixth term, well, you could just use your formula. You could expand this. I'm not going to right now to save us some time. So questions 6, 7, and 8 are extra creative ones. I think we have time to do 6. I will ask you to do 7 and 8 for Tuesday. Right? That's our next class after this one. I know, so sad. Miss Friday. Okay? So in this expansion, the sixth term contains an x to the 16, and now you're finding the value of n. So a little bit different than what we've done before. We've never in a grade 12 question did they ask you to solve for the exponent in a binomial expansion. So we can write out everything that we know. We know it's the sixth term, so it's going to be n choose 5. But what we don't know is n. So it's a little bit of working backwards in the ones where you know n and say find out which term has an x to the 16. And you were finding r. Now you have to find n. So using that same idea, we can ignore the coefficients. And then solve for n. Multiply both sides by x to the 5, or subtract on this side. Blah, blah, blah. N is equal to 12. All right, so this is where we'll stop.